Okay, we're going to do a few examples from section 3.4. We're going to determine where the function f is concave up, where it's concave down, and where it may have any points of inflection. So we're going to start off with a nice easy example of a beautiful polynomial function. They're nice and friendly functions. They're everywhere continuous, everywhere differentiable, twice differentiable, whatever, how many times you want to take a derivative, we can go ahead and do that too. But we have this function, 2x cubed minus 5x squared plus 3x minus 1. We want to determine its concavity and also any points of inflection. So we're going to go right for the first derivative here. There's going to be 6x squared minus 10x plus 3. The first derivative is not going to give us concavity, so we're going to have to continue on to the second derivative. Second derivative is going to give us 12x minus 10. And 12x minus 10 is everywhere defined as well. So my second derivative, as well as my first derivative, everywhere defined. I need to now figure out where my second derivative is going to equal 0. So I set the second derivative equal to 0 and solve for x. And I get x equals 10 over 12. And that reduces down to 5 over 6. So if I do have a point of inflection, it has to happen when x is equal to 5 over 6. So we're going to draw ourselves a little number line here, mark our positive and our negative infinities, and we're going to just hit 5, 6 right here. And by putting one number in the middle of our number line, we have divided the number line up into two different intervals. So I'm going to make a little chart. Here are my intervals. Here are my test points. Let's see what we have here. First interval is going to go from negative infinity all the way to 5, 6. Don't let that 5, 6 scare you. You really don't have to work with it much. And then when x is 5, 6, we're going to break, and we're going to go from 5, 6 all the way to positive infinity. Now, one test point that's on this first interval would be a negative 10, and a test point that's on the second interval between 5, 6 and a positive infinity would be a positive 10. We're going to take those test points like we did with our first derivative test. We're now going to put this into our second derivative. So we are going to use these test points with the second derivative and see what it is we have. The second derivative is not in factored form, so it's just as easy to plug the numbers in. If you didn't want to pick a negative or positive 10, you didn't have to, but 12 times negative 10 is negative 120. Take away 10 more is negative 130, so I'm just going to write negative 130. I know that that's less than 0. Because it's negative, so what does that tell me about the original function itself? The original function has to be concave down because I have a negative second derivative, and a negative second derivative tells me that the function is concave down on that interval. I'm going to take a positive 10, plug a positive 10 in. 12 times 10 is 120, take away 10 is 110, I'm sorry. That's greater than 0, so that tells me that this function is concave up on this interval. Okay, so I need any intervals of concavity that are concave up or concave down, or any points of inflection. I got a little bit of room right here so I can write something on this side. I'm going to say that f is concave up on, let me see, concave up on 5, 6, comma, infinity, on that interval. I'm going to tell you why. It's going to be because my second derivative is greater than 0 on that interval. I'm going to also mention that f is concave down on negative infinity to 5, 6. Why is that the case? Because f double prime is less than 0 on that interval. Anytime you want to tell somebody that a function is concave up, your reasoning is always because the second derivative is positive. If you want to say the function is concave down, your reasoning is always because the second derivative is negative. And you can write is positive or is negative, but that's just a faster, quicker way. So do I have a point of inflection? F has a point of inflection at a point on the graph where the function f switches from concave down to concave up, or concave up to concave down, but in this case we're switching from concave down to concave up because we definitely read the graph from left to right. And that x value on the graph is 5, 6. So I'm going to say at 5, 6, comma, and now we actually need to take the number 5, 6, unfortunately, put it back up into the original function, and if you feel like it, you can do a synthetic division by 5, 6 with 2, -5, +3, and -1. And you can do this synthetic division and come up with this answer. Whatever the remainder is, that's going to be the y-coordinate when x is equal to 5, 6. So I do have this done on my paper, so I don't have to do it out a little bit more for you, but 5, 6 times 2 is going to give me 10, 6, which reduces down to 5/3. And I take a -5 and I add 5/3, it's going to give me a -10/3. I take 5, 6 and multiply it by a -10/3, and I get -50 over 18. And I add 3 to a -50 over 18, that gives me 4 over 18, which reduces down to 2/9. And then 5, 6 times 2/9 is 10 over 54, which I suppose I could reduce. I didn't reduce it on my paper, so I'm not going to reduce it now. And this gives me a -44 over 54, or a -22 over 27. So therefore my point of inflection is going to occur at 5, 6, comma, -22 over 27. And all of this information is what I asked you to find, so this whole entire thing gets boxed. So we have an interval of concavity where you concave up, concave down, and we do indeed have a point of inflection. Be careful though, we don't always get a point of inflection just because this changes from concave down to concave up or concave up to concave down. We have to make sure that this x equals 5, 6 value is actually a point on the original function. If it's not a point on the original function, then it will not be a point of inflection on the original function. Okay, so we're going to wipe that off. I'm going to put another example on the board. We're going to call it example 2. And I think this time we'll go for a rational function. I could leave all this there because I'm certainly going to fill in another chart, but I'd have to erase all the different entries, so I might as well start all over anyway. So here is my example 2, and we'll switch to a rational function. Let's get something like this, -1 over x minus 3. It's an easy rational function. You should notice some asymptotes real fast. This function is definitely bottom heavy, so we're going to have an x-axis or a line of y equals 0 as our horizontal asymptote. We might not care about that, but we might, so I thought I'd write it down. We're also going to have a vertical asymptote. You can see that when x equals, I want this to be a +3, so when x equals -3, we're going to go ahead and have a vertical asymptote because a -3 was going to make this denominator equal to 0 but not make the numerator equal to 0. I won't have any holes or anything, so. And I pretty much have an idea of what this looks like too. I know what the graph of y equals 1 over x looks like. I know what that would look like if I shifted it to the left by 3 units. And I know what it would look like if I negated it and reflected it over the x-axis. So I would have a rough idea of what it looks like. However, I don't want you graphing this to determine the points of inflection or the intervals of concave up or concave down. I want you to grind the math out and let the math spit the answer out for you. Okay, something I'd like to mention is that x is not going to equal -3. I need to make sure that that is big in my head because it didn't tell me anywhere that x wasn't a -3, but I cannot have a -3 in the domain of my function. So if I work through this whole process and I come up with the fact that I think x equals -3 is the location of a point of inflection, I will be wrong because that -3 is not even defined in the original function. So I want to make sure I'm aware of that, and I gave myself a big circle so I'm not bound to forget it. So let's go ahead and I think I'd like to rewrite this function. I'm not too crazy on the quotient rule, so I'm going to rewrite this as -1 times x plus 3 to the -1 exponent. Now I'll just use power rule. First derivative is now -1 times -1 is a +1, x plus 3 quantity to the -2. The second derivative, -2 times a +1 is going to give me a -2 times x plus 3 to the -3. Now, I know I didn't say this out loud to you, but in my mind, I did actually think times 1 right there, because the derivative of x plus 3 is 1. So this was my chain rule. I didn't talk about it. I should have, and I should do it again right here and say the derivative of x plus 3 is a 1 again. But just keep it in your mind that I did think about it. So this is the same as -2 over x plus 3 quantity cubed. Once again, you can tell that this second derivative function is not defined when x would equal -3. Of course, the original function isn't anyway, but that's okay. Also, there's no way I'm going to get this second derivative to equal a 0. So if there's no way that I could possibly make this thing equal 0, this will give me x plus 3 quantity cubed, which means that 0 equals -2. When will 0 equal -2? Just write never. It's never going to happen. So I'm not going to ever get the second derivative equal to 0. Which means that I need to make my number line based on only the point of discontinuity, which is going to be at -3. So here I'm going to have my intervals, or interval, I don't care whether you put an S there or not. We're going from -infinity to -3, and then we're going to go from -3 to +infinity, and we are going to draw this line here, x equals -3. Okay? Okay, now we need a test point. I'm going to go for a -10 and a +10. They tend to be my favorite numbers to play with for some reason. After I do my test point, I'm not interested in that first derivative stuff right now. I'm interested in second derivative because we're talking about concavity and points of inflection. So key in on the fact that when that happens, you need a second derivative with your test points. Okay, so my second derivative function is over here. Let's go for it right here. The numerator is always going to be a -2 no matter what x value I substitute into this function. So the numerator is always going to be negative, and if I put a negative in here, -10 plus 3 will give me a negative number. I cube a negative number, and I'm going to get a negative number. So that's going to end up being a negative value divided by a negative value, which is going to be positive. And positive values are, of course, greater than 0, so my original function is going to be concave up at, or anywhere on this interval between -infinity and -3, because the second derivative is greater than 0. Now when I put a 10 in, notice, I'll just keep that as a negative, not a -1, because it's really -2. Put a 10 in here, and 10 plus 3 is 13. You cube that. I really don't care what it is, except the fact that it is positive. A negative divided by a positive is a negative, and that is less than 0. Therefore, my function is concave down on that entire interval. Okay, what do I know? I know f is concave up on -infinity to -3. And I know that that's true because why? The second derivative is greater than 0 or positive. I know that f is concave down on one interval between -3 and +infinity. And why do I know that? Because my second derivative is less than 0. And do I have an inflection point? I switched from concave up to concave down. So I'm thinking I have an inflection point, and I wonder where that is. I look up between concave up and concave down. That gives me x equals -3. So at x equals -3, you're thinking you probably have an inflection point, and then you pause and you say, wait a minute, x can't equal a -3 because it's not even a point in the domain of my original function. So therefore, you do not have an inflection point at x equals -3. As a matter of fact, f does not have an inflection point. And you can say because there is no point where f changes concavity. There is no point on f where concavity changes. Okay? We definitely concavity changes, but there's no point on f where the concavity changes. And therefore, our answers are here. Okay, we're going to let that go and see if this video will upload.